In this module, let us prove that the set R is uncountable. We will use the nested intervals property again to prove it. The common proof given in most textbooks is via decimal expansion of real numbers. Since I have not made precise the decimal expansion of real numbers and doing so is quite tedious, I prefer to use this approach. Theorem. R is uncountable. Statement is simple enough. Let's prove this. Proof. Suppose we have a list of real numbers S1, S2, S3, so on. Okay. Let I1 be some closed interval that does not contain S1. Well, why does such an interval exist? Well, that's obvious. Say S1 is here, just choose some interval like this. Fine. Now, so this is I1. Let I2 subset of I1 be another closed interval such that S2 does not belong to I2. Why does such an interval exist? Well, again, just choose, so say S2 is here, just choose this interval. Okay. Now, consecutively, choose Ik subset, or rather Ik plus 1 subset of Ik such that Sk plus 1 is not an element of Ik plus 1. This can always be done. Consider intersection of Ik's, k running from 1 to infinity. This is a non-empty set. Non-empty set by nested intervals theorem. Okay. Let S be in this intersection, which I'll just call I. Let S be in I. Then S is not there in this list. Okay. So what we have done is we have started out with the list S1, S2, S3 of real numbers and have shown that there is some element that is not there in this list but is a real number. Okay. So this proves that there is no way to list out the real numbers, and if you recall our discussions on cardinality, listing out the elements is another equivalent condition for being countable. So that means R is uncountable. So the set of real numbers is an explicit example of a set that is uncountable, and this also shows that the number of real numbers that are there exceeds the number of rational numbers in some sense, because the rational numbers is a countable set. This is a course on real analysis, and you just watched a module on the uncountability of R.